Today we're going to be talking about the powers of complex numbers, and your learning target today is using De Moivre's theorem to find the power of a complex number. De Moivre's theorem is the very first thing we're going to go over. It's right here. Let z be the trig form of a complex number and n be a positive number. Then z to the n, so that trig form to the nth power would be the entire trig form to the nth power, or simplified, and this is De Moivre's theorem, r to the nth power, so that power gets distributed to the r, and then it becomes a multiple of your theta. So this second formula, part of the formula, is what we're going to use as De Moivre's theorem to find the power of the complex number. So we take the power of r, and then we take the multiple of theta. One quick hint: when we're finding the power of a complex number, you need to have it in trig form first to apply De Moivre's theorem. Notice this is all in trig form. There's no standard form, no a plus bi. So if you're given a plus bi, you must convert it to trig form first and then use De Moivre's theorem. Okay, we've only got 3 examples because these are a little more lengthy than some of the other examples that we've done. Okay, so we start off with a trig form of a number to the 5th power. De Moivre's theorem says that we can write this as 3 to the 5th times cosine of 5 times 3 pi over 2 plus I sine of 5 times 3 pi over 2. Okay, that's going to be 15 pi over 2. 15 pi over 2 is my angle. So I have 3 to the 5th, which is 243. You can use a calculator for that. And if I were asked for my answer in trig form, I would be done. However, our directions ask us to write our answer in standard form, a plus bi, which means I need to simplify the 15 pi over 2. So I'm going to start off by distributing that 243 to the 2 parts of my parentheses. So I have 243 cosine of 15 pi over 2 plus 243 I sine of 15 pi over 2. Well, it's going to be helpful to know where 15 pi over 2 is. So we think about our graph. 2 pi is 4 halves. So I'm going to go 1 circle for 4, 2 circles for 8, 3 circles for 12, 4 circles would be 16, so I'm 1 pi over 2 short. So I end up down here at this lovely point on the y-axis, which on our unit circle would be 0, -1, where the 0 stood for cosine and the -1 stood for sine, and I can plug those values in. 243 times 0 plus 243i times -1. The 0 is going to cancel out the first part, and I'm going to end up with -243i as the 5th power of that complex number. Okay, example 2 comes in standard form this time. So we need to convert it to trig form first. So you're going to think about your r being the square root of a squared plus b squared, which is the square root of 4, so you get 2 as your r. Then you have to come up with your theta, which is the inverse tan of the opposite over the adjacent. That is a ratio we recognize. Tangent is positive in the first and the third. This positive is going to be a first quadrant angle, so I know I'm looking in the first quadrant where the a is. Square root of 3 over 1 is 30, 60, 90 with a 60-degree reference angle. It does not matter whether we write it in degrees or radians, because my final answer is going to be in standard form anyway. So I'm going to use a theta of 60 degrees and an r value of 2. So I'm going to get that 1 plus I radical 3 cubed is going to be my r cubed times the cosine of 3 times my theta plus I sine of 3 times my theta. Since we're looking for our answer in standard form, we're going to multiply these together. We're going to take the power. We're going to end up with 8 times the cosine of 180 plus 8I times the sine of 180. I need to evaluate 180 degrees, cosine and sine. 180 is the point -1, 0 on our unit circle. That represents cosine and sine. So I get 8 times -1 plus 8I times 0. Anything times 0 goes away. I end up with -8 as the third power of this complex number. So I just want to point out that you can end up with a real number from powers of a complex number, because part of it was real and part of it was imaginary. And if you take certain powers of imaginary numbers, you can end up with real numbers. Okay, final example for the day. 1 minus I to the 4th power. Start off by putting it in trig form by finding r and theta. R is going to be the square root of your a squared plus your b squared, which is going to be the square root of 2. Not the prettiest in the world, but we can deal with it. Your theta is going to be the inverse tan of the opposite over the adjacent, which is -1/1. Think about where tangent is positive, ASTC, positive here and here, so I cancel those out. 1, -1 would be in this 4th quadrant, so I'm going to focus on the 4th quadrant angle. 1, 1, square root of 2 is going to be a 45-degree reference angle, so I'm going to use my theta as 315 degrees as that 4th quadrant angle. Okay, so then I put it into my formula, and I have 1 minus I to the 4th, r to the 4th times the cosine of 4 times my angle, and here's where it gets a little more difficult. Square root of 2 squared would just be 2, so to the 4th it's just going to end up with a 4. Here's where our choice of 315 degrees may be a little more difficult, because if I multiply that by 4, then that becomes a pretty big number. So let's think about this instead of 315 as -45 degrees, because that's the same angle, and it's going to be easier to multiply the 4 times -45 degrees. Okay, that's going to get me cosine of -180 plus I sine of -180. Okay, we want our answer in standard form, so I'm going to distribute. I'm going to have 4 cosine of -180 plus 4I sine of -180. We have to evaluate that -180 degree angle. That would be over here, again at the point -1, 0, where cosine is -1, sine is 0. So 4 times -1 plus 4I times 0. It's going to cancel out the 4I, and you're going to be left with -4 as your power of 1 minus I. So again, we end up with a real answer from an imaginary or from a complex number power.